Alright, so now finding area under the curve, the theory behind it, in general function cases. Alright, so we looked at sort of a special case in the last set of notes. And so now we're going to look at another example in a general case. So if I'm given a function, a positive function means it's a function where it's graphed above the x-axis. And so I think it's easiest to look at this in an example. Alright, so I'm picking the function f of x equals x squared plus 1 over the interval 0 to 2. Alright, and so that's what I have graphed here. Alright, so this is the function. Alright, and it's from 0 to 2, right? So those are the edges. So this is the area we want to find. Alright, the area of my function between 0 and 2. Alright, so at this point we can't do this exactly, but I'm going to use the Riemann sum method to approximate it. Alright, so I'm going to estimate the area by dividing it up into smaller regions and drawing rectangles over those regions using the left and the right points. Now technically, like I said before, you could use any value in each of my intervals, but the easiest ones are on the left side and the right side. So those are the ones we're going to stick to in this class. We're just going to stick to the simple cases. Alright, so first of all, I want to divide my area up evenly. Alright, so I'm going to take my area, which is between 0 and 2, right? That's the area I want to find. Alright, over 0 to 2. But I'm going to break it up into smaller regions, smaller areas. Alright, and we want to make sure when I break it up into smaller areas, I make them equal distant, alright, and equal width apart. And we do that by doing this process. Alright, so I take my endpoints, my A and my B would be my endpoints. N would be how many rectangles I want to draw. Alright, where I'm going to draw my different areas. So those would be my N subintervals, where I'm going to divide it up into N little areas. Alright, my N little areas are my N little rectangles. Alright, so this delta x, which means change in x, that's the width of each region, which represents the width of each rectangle. Alright, the height of each of my rectangles will come from my function values. Alright, I'm going to draw my rectangles, and they're going to hit the part of my function. And what part they hit, alright, that'll be the height. Alright, my function value, the y part, right? The y part of the point is my height. Alright, so again, the easiest thing to do is to set up the example. So I'm going to draw it with the example that we gave you before. So my function f of x, which is x squared plus 1 over the distance 0 to 2, over the region 0 to 2. Suppose I want to divide it into 4 areas. Alright, so 4 rectangles. Well, I have to divide the big interval. Alright, so this is where I want to find. That would be my area I'm looking for. But I'm going to divide it into 4 smaller areas. Alright, and so in order to do that, I make sure they're equal distance apart, equal width. And so I take my change in x, which represents my width. My A and my B are my endpoints 0 and 2. So I take 2 minus 0, divide by how many rectangles I want, which are 4. So 2 divided by 4 comes out 1/2. So 1/2 is my delta x, which is my width. Alright, which means I'm breaking down the area between 0 and 2 into 4 smaller areas. Alright, so 4 subintervals, meaning that's the areas broken down into these 4 spots. Alright, that would be my first area, my second area, my third area, and my fourth area. Alright, and if you look at these, each of these have a distance of 1/2, right? 0 to 1/2, 1/2 to 1, 1 to 1.5, 1.5 to 2. Alright, so each of those have the equal distance of 1/2 a unit. Alright, now we can draw our rectangles. Alright, so each of those areas are going to represent a rectangles, and I can draw them one of 2 ways. Again, there are infinitely many ways I can draw my rectangles. We are only going to draw them 2 ways, using the left endpoints of my region and the right endpoints of my region. Alright, so I drew the picture here in your notes. Alright, so we start off with the right endpoint, so this would be the right Riemann sum. And so the red line is my function f of x over the interval 0 to 2, where I've graphed my rectangles over each subinterval. So if you look here, here are my subintervals, right? 0 to 1/2. Actually, I'm going to write them underneath. So this would be my first interval, 0 to 1/2, where my first rectangle is. Then my 1/2 to 1, 1 to 1.5, 1.5 to 2, right? Area 1, area 2, area 3, area 4. Where the width of each of those is 0.5, right? Each of those have a width of 1/2. Right? That's the distance between. The heights of each of my rectangles come from my function value. All right, so the height, you look at the red line, the height comes from my function value, and I start on the right side, which means I'm starting over here at the 2. This is the right side. And so this is my first rectangle. It's going to come up here and hit this point on my curve, right? And so this point is my function value, my y value, at 2. All right, well, my y value at 2 was 3, right? This height is a unit 3. Or not 3, sorry, 5. 5, not 3, right? I plug 2 into this equation. I get 2 squared, which is 4, plus 1, which gives me out 5. So f of x is x squared plus 1. When I plug 2 in, I get 5. All right, so this distance here is 5. And so there's my first rectangle, which would be the height of 1/5, the width of 1/2. All right, now this rectangle here. All right, starting on the right side, so this is the right side of it, where it's going up and hitting this part of my function, that part of my red line. All right, and so that height would represent my function value at 1.5. So again, I take 1.5 and plug it into my function to find that height value. When I plug 1.5 in, it comes out 3.25. All right, so that distance here is 3.25, that height. All right, now this rectangle, all right, this is the right side of it that we're looking at. It hits this part of my function. All right, that part of my function is at 1, so I find my function value at 1. Well, when I plug 1 into my function, it's 1 squared plus 1, which is 2. And so this height is 2. All right, then my last rectangle, again, I'm on the right side. It hits this part of my curve, which, again, using the 1/2. So these are the values I plugged in. All right, so that's why my function value at 0.5 comes out to 1.25, and so that height is 1.25. And so I find the area of each one of my rectangles. The area of the first rectangle is going to be 1/2 times that height, 1.25. Then the second rectangle is going to be 1/2 times 2. The third rectangle is going to be 1/2 times 3.25, and the next rectangle, the last one, 3, 4, is 1/2 times 5. And I have that actually written later in my notes. All right, so this is sort of what's going on picture-wise, and then writing it all out. All right, so the height of each of the rectangles is determined by the function value at the right end point. All right, so the right end point is nothing more than the y value at that end point. All right, the area is estimated by adding up each rectangle that we have drawn. And so my area is approximately, so if I write this out, this was area 1, this was area 2, this was area 3, this was area 4. All right, which I found those values. 1/2 is the width, right? 0.5 equals the width. And then the function value is the height. All right, the function value at my end points. All right, so this would be an end point. All right, so my first rectangle was at the end point 1/2. I plugged 1/2 in. That came out 1.25. So there's my width and my height, and so that's my first area. And then the next one was at 1/2 times 2, 1/2 times 3.25, and 1/2 times 5. And so again, area 1, area 2, area 3, area 4, right? Those would be those 4 rectangular areas using width times height. All right, when you multiply that out and simplify, it comes out to 5.75, which is a high estimate. My actual area should be less than that. My actual area would be less than 5.75. If you look at the picture, so I'm going to scroll back up to the picture, you'll notice that there's some area above my curve. So that means the area should be less than it because I've got extra area that lands above. All right, so that would be the right side area. Now the left side area. All right, so again, we don't have to necessarily take rectangles values from the right. We can also take them from the left. You could actually take them at the midpoint or any value in between. We're not. We're just going to stick with left and right because they're the easiest ones to find. and understand. All right, so now the left side, the left-hand Riemann sum. Same function, so the beginning of this is the same. I'm still looking at this function. The actual area I want to find is from 0 to 2, but I can't find that exactly yet. What I do is break it up into 4 smaller areas, right? 4 subintervals, which means 4 smaller areas. Each of them will have a width of 1 unit, or half a unit. All right, and again, that's all the same thing we did before. This is still area 1, this is still area 2, this is still area 3, area 4, but I am going to get different values for each of those areas because I'm going to be using a different point. All right, so the picture, using the left side. All right, so the red is still, this is still my function, f of x is x squared plus 1. But now I'm drawing my rectangles starting on the left side. And so my first rectangle came up and hit here, right, on the left side. The next one came up and hit here, and so on. And then that was my last value. So this will be a low estimate because I've got area above I didn't find, right? The green area is what I'm finding. This would be area 1, that would be area 2, area 3, area 4. The width is still 1/2. There's 1/2 unit between all of these. 0.5 is the distance between each one of those, right? That would be the areas drawn between a half a unit. The heights, though, are different because now I'm looking on the left side. So if I start with area 1, I'm now on the left side. Well, my left side hits my curve here, where I'm plugging in the endpoint 0, right? My function value at 0, which is 1. So the height of area 1 is 1. Now the height of area 2 is on my left side, which is 1/2, so it comes up here. Well, I plug in my 1/2, that came out 1 1/4. All right, so that was the height of that area. Area 3 comes up and hits my value at 1, which was 2, so this area's height is 2. And then the last area comes up and hits it. I use 1 1/2, which is 3 1/4 when I plug it into my equation. All right, so this was 3.25 was this distance here, this height. All right, that's the function value, all right, at each one of those. All right, so those are the areas we're going to find, my height and my width. And so we find them, so using the left. So area is estimated using the left endpoints drawn above, adding them together. And so here's what it is. All right, so the first area is found, all right, so that would be area 1, right? Half a unit's my width. My height comes from plugging 0 in, so that's 1. That's where this 1 comes from. Then my second rectangle is this one, where my width is 1/2. My height is found by plugging 1/2 into my function, which is 1.25. And then my third one is this one. My distance here is still 1/2. My height here is still 2. And so that's my 1/2 times 2. And then the last one, area 4, would be this last rectangle where my height is at 1 1/2. Found plugging 1/2 into my function comes out 3 1/4. All right, and so there are my values. Area 1, area 2, area 3, area 4. When I multiply them out, it comes out to 3.75. And remember, this is a low estimate, right? I'm missing the areas above. And so in this case, this estimate will be an underestimation because each rectangle is missing some area above it. The actual area then would be bigger than that 3.75 and smaller than the first area we found, 5.75. All right, so the actual area is somewhere between those two values. But if you'll notice, that's still a fairly big gap. Right? There's a 2-point difference between my low estimate and my high estimate. And so what we'll do, well, what if I can get a little better? Well, how can I make that area a little nicer? All right, how can I make that region a little closer to the actual value? Well, suppose we want to get a little bit better estimate. All right, because the estimates above really didn't do that great of a job. There's a whole lot of area above and a whole lot of area missed out. All right, there's a 2-unit difference between the two, which in that case was a fairly big error. So what if I doubled the number of rectangles? Instead of 4 rectangles, all right, I doubled it to 8, which means I broke my area down into 8 areas, all right, which means 8 rectangles were used. And I have the pictures here. All right, this would be area 1, area 2, and so on. Area 3, area 4, area 5, area 6, area 7, area 8. Same thing here, all the way up to area 8. So this would be my right. This would be my left. which again, I've drawn them. My width is 0.25. You find my width, right? That's the change in x where I take my lower value, or my b minus a over n. So delta x would be 2 minus 0 over 8, right? I want 8 rectangles, which comes out 1/4 or 0.25. And if you look, each of those are 0.25 units away from each other. The width of each of those is 0.25. The height is found by my function value. Depending on which endpoint I'm looking at, right? This one would start at 2. The next one would be over at 1.75, and so on, and we'd find all my different heights. And then add up my areas once I find those. I'm not going to make you do that. I'm not going to go through it. I'm just going to find them for you. So again, that's the process. Once we went through the process, this is what you find. The area of the 8 rectangles on the right side was 51. So this comes 5.1875. The area on the left was 4.1875. And so now our actual areas are only 1 unit apart. Right, my high estimate is 5.1875. My low estimate is 4.1875. And so the values are a little closer together. Right? They're becoming closer and closer to each other. There's only 1 unit distance between them than there was in the previous answer where there's a 2 unit distance between. So this is a little better. My area, I'm a little closer to what my actual area is. All right, well, suppose I divided it into more rectangles. All right, and so I went ahead and divided it into 100 rectangles. And I only drew one of them because, again, they basically look like the same picture. All right, but there are 100 rectangles here. If I find the width of each of my rectangles, I would take my 0 divided out by my n, which were 100 rectangles. And so each rectangle has a distance of 1/2 between, or 2/100 between them. All right, so they're very close together. All right, they're not very far apart. There's a whole bunch of rectangles. And if you look in here, that looks like it's found my area pretty good. Just based on the picture, it looks like it should add up to my sum. All right. And so these are the values that are found. And again, I only drew one picture because they look basically identical when I drew them in the program. The left area was 4.6268. The right area is 4.7068. So my actual area was between 4.7068 and 4.6268, which those values are really close together. I actually found the actual area. The actual area was 4.6 repeating, so 4 2/3. And so these are pretty close. Once I've got 100, so suppose I did 1,000 rectangles, I get even closer, or 10,000 rectangles, or 1 billion rectangles. 1 billion rectangles would probably give me an answer that rounds to the actual answer, right? The more rectangles I get, my left side and my right side converge to the same value. My left-hand areas and my right-hand areas will converge to the same number. And so this is what we're going to get. We're going to get a limit of this. All right, we find that as we make more and more divisions, smaller and smaller rectangles, each with a width that gets smaller and smaller, right? Every time I add more rectangles, the smaller the width of each of my rectangles is. We can make them so small that they basically approach 0. Now, they can't get to 0 because my area would 0 out, but what they do is they can get as close to 0 as anybody could ask me to get. When they do approach 0, the area of the sum from both the left and the right side approach the actual area of my function. And so that's a limit definition, right? Let's say as I'm approaching something, so my function is behaving in such a way. In this case, it's the sum of my rectangular areas. Alright, so that brings us to the following limit. If I have a positive continuous function, so it has to be continuous, no holes, gaps, or asymptotes, from some point A to some point B, positive means it's drawn above the x-axis. Alright, the limit of the Riemann sum exists, meaning I can find left hand, right hand, I can find any sum. I don't have to be left or right, I can find any of them. Riemann sum is just finding the rectangular areas. Alright, and I can use any rectangular areas I want. Now we just did left and right. So that's what this means, all choices of n. Over n sub intervals of equal width, where we find them using this delta x. Alright, the limit of the sum of the area of the rectangle is found by this limit, so it's the limit as n approaches infinity, alright? More and more subintervals, more rectangles. If n approaches infinity, that fraction approaches 0, right? Those fractions get smaller and smaller and smaller until they approach 0. Of my Riemann sum is the width times the height of my functions. Well, delta x represents the width, so it'd be delta x times all of my function values. Right? And so what's inside the limit is the Riemann sum, right? So the Riemann sum is, remember, delta x represents the width of each rectangle, right? The width of each, subinterval. F of x is the function value, right? F of x is the function value, which would be the height of each rectangle. And what it comes down to, since delta x is approaching 0, right? The width between each of my function values is basically 0 in a way. Make it so small that it's as close to 0 as anybody could ask me to get. What's happening here is this is the limit of an infinite sum. This is the limit of as n approaches infinity, so it's infinite. And this will be the accumulated sum of my function value. From A to B, between A and B. So if you go look at the picture that I had drawn up there before, which is equal to my area of f of x over A to B. Alright, so that's what this is a big limit. This is a big idea. Alright, it's a limit of an infinite sum. And the reason why we call it the limit of an infinite sum is because basically I'm adding up every single function value between A and B, because this delta x that's out front is basically 0, or approaches 0. It's so small it doesn't matter. And so all I'm doing is adding up all of the function values from point A to point B. And if you go look at that picture, this one, that sort of looks like what's happening here, right? And this is just if I have 100 rectangles. Suppose how this would look if I had 1,000 rectangles. But it's basically just adding up 100 function values, right? That's what it is, 100 function values, and then multiplying by this distance, which is fairly small. All right, well, suppose the distance was, suppose I had, like I said, 1,000,000 intervals, so I would take my 2 and divide by 1,000,000. Well, that would be fairly small, right? That distance would be very, very small, really close to 0. If I go to 100 million or a billion, that would be even smaller every time I put another 10 rectangles in there. And it comes out further. And so this is so small that basically I'm just accumulating all of my function values. I'm adding up my function values. That change in x doesn't really matter. All right, and that's what that listless limit is finding. All right, the limit of the sum of the area is equal to the area of my function from point A to point B, which really is an accumulation of all my function values between point A to point B. Alright, now like I said, we keep it fairly basic in this class. I'm giving you the theorem. We're not unlike the derivative where we solve the limit definition of the derivative. We will not be solving this limit. It requires more algebra skills than what we require in this class. It's very difficult to do by hand, and so we won't be. But you need to understand it. You need to understand what it is and what it's finding. Because like I said, this is the foundation for what we're going to do for the rest of the semester. Alright, so this is the foundation for the definite integral, which is looking at area and the accumulation of my function values. Alright, so we'll stop there. we're still going to do one more part of this where I'm going to do a couple more examples of the first case that we looked at, because again, you have to use this method in the first case. Alright, but we're going to stop there with this theorem and then pick it up in my next set of notes.